Okay, so far, I mean, we had rather simple examples, free particle, harmonic oscillator. So now we are going to do something more elaborate, which is introduction to non-perturbative methods, or one non-perturbative method, which is related to what we did last time, which is say, well, we can understand actually the path integral or the propagator. We can look at this object as not being defined for some real time, but we may allow for complex times. Now, if we allow for complex times, we have immediately the relation to quantum statistical physics. So this is one nice thing. Now here I want to discuss an example where this idea of allowing for imaginary or general complex times is essential to solve a problem. I mean, problem probably all of you have already solved in quantum mechanics using WKB methods. It's a tunneling problem. But I think the path integral method here is quite nice, and the strong thing is that you can again generalize these concepts from simple quantum mechanics to quantum field theory. Okay? So that's the idea. So what we want to study as an example for such non-perturbative methods is tunneling in a double wall potential. So you have here, I draw some potential in your cube, and you have some potential which has two minima. Just to have one example, which we will discuss then as one concrete example is this. But the thing is that all we are going to discuss does not rely on one specific potential like this one given here, but for illustration it's good to think of one. But what we want to just discuss is such a potential where you have two minima, and the question now is assume that the kinetic energy of the particle is much less than the height of the variable. Okay, so I have some particle trapped in some minimum, and the kinetic energy is very, very small, such that it cannot simply overcome this barrier here. Okay, so that's the situation, and the question that we want to ask is, what is the probability that the particle will tunnel from one minimum to the other? Probability for tunneling. So what we want to calculate is, let's give this some coordinate. This is, let's say, centered at minus a, and this is at a. That you start with an initial position a, and you propagate under the Hamiltonian in time and find a finite amplitude for the final state to be in plus a. If we square this, then we get the probability, and this is the probability for propagation from a minus a times t. Okay, so this is just what we want to calculate. Now, what we want to consider is, in a way, this probability in some long times, and long times here, I will come back to this. So you have some characteristic time scale defined in the problem. This is, you can see that you have here minima, so there the potential is just as a form of a harmonic oscillator, so it's quadratic, and then the curvature gives you some natural time scale in the problem. Okay, so that's like if you think of a harmonic oscillator, you have m omega q squared around here, so the omega defines in the problem, which is given through the curvature, defines with some energy, and this energy defines a time scale. And we will be interested in time scales longer than this intrinsic time scale here. And what we can look at, just to give you an idea already, well, you could try to solve this kind of problem in some semi-classical limit. Yeah. So this is also, I think, what I don't know if you do it, but like many quantum mechanics courses, you solve this kind of problem using the WKV method, which is also a semi-classical method. Okay? So if you just take the semi-classical assumption, well, you see, well, you can represent the amplitude as said as a path integral propagating from minus A to A. Yeah? So we want to see particle, let's say here, in the probability for tunneling. And the question is, what is the probability to propagate to A? So if you would start just using let's say, the path integral in the semi-classical approximation, what we should do is we should solve semi-classical equation of motion, but of course in this regime we don't have any solution. Okay? So then comes the idea, well, if we allow for imaginary times, we can, instead of calculating this object for t being real, we can take this more flexible, complex number, and this then allows for looking at solutions. And these solutions are of topological nature, as I've been discussing. Okay, so that will be the problem. As a first step, I think it's good to get some intuition of the problem, and this is always like, before we go into the calculation, just take let's take a very simple model to see what we already can say about this kind of problem. And then we can afterwards, if we have like microscopic way how to calculate this, we can see how good the simplified model is, and this also allows it to fix parameters of the simplified problem. Okay? So what is the simplified model? So let's consider a cartoon of this problem, which is just following. So let me draw this double wall potential, and we have here position I, minus A and A. We have here some height in energy, which is V0, and let's just consider the following. Let's say we have the particle sitting here and the particle sitting here are just two states. Okay, so let's just map the problem here to a two-state model where the particle can sit here or here. This is associated with some energy, and then there is some hopping element, some transition element, which allows you to hop from this state to this. Okay, and this we are considering is quite small. Okay, because the height is much larger than the typical energy. So let's consider just two levels. With energy epsilon 0. So this is a symmetric potential. So we have here two energies, epsilon 0, which are the same. The general problem. So if we wouldn't have any tunneling, if this was infinite, we'd just have the general problem of particles sitting here or here with the same energy. But now we have finite possibility to tunnel. So we have some tunneling element, which we call delta epsilon, and this is assumed to be small. So we have a weak perturbation. Okay? So we can immediately write down the Hamiltonian for this problem. So the Hamilton operator is just given by diagonal parts given by the energies epsilon 0. And this corresponds just to the particle sitting 0 here. And then we have the hopping term, which makes a transition from minus A to A or from A to minus A. Okay? So this is a sketch of the problem. And now what we can do is, well, we can, under the assumption that this is somehow a good description, we can just calculate this transition probability. Okay? So, well, first we can rewrite the Hamiltonian, if you like, just in some matrix. Simpler, where we used represented the states A and minus A by some vectors. So this we use as a basis. And we can, well, first just calculate the eigenvalues and the eigenstates of the problem. So the eigenvalues, let's call them epsilon plus minus. So 0 plus minus delta epsilon. So, okay, you know all the trick. Also the trace gives you the sum of the eigenvalues and determine the product. So we have the trace is 2 epsilon naught, and the product is epsilon naught square minus delta epsilon square. And the eigenstates using this basis. Now, given this, we can simply calculate this transition amplitude. Well, inserting these objects, we can use that the Hamilton operator, or we can write the time evolution operator is diagonal in this basis. We have the eigenvalues, and we just have to calculate the overlap and find the following. So with this, we find that the propagator A H bar minus A is given by a phase factor which just takes into account this is a minus I, which is just the oscillation with the average energy. And then we have a term which vanishes for vanishing coupling between the two. So if delta is 0, of course it should vanish. And this is just, I mean, the dynamical phase given by the average energy. And this is which will give us rise to the transition probability. So this you can just check by using the eigenvalues and the eigenstates. And to find the probability now, we have to square this. So the probability to path from minus A to A in a time t, according to the simple model, is given by sine squared delta epsilon t over h bar. Okay? Where now the result depends on this phenomenological parameter delta E that we introduced. And we have just the periodic probability. Now, what we want to do, well, this model kind of, I mean, this is the standard model of like a two-level system. Also, you have like, you start, let's say, from a simple two-level system, which are not speaking to each other, and then you can introduce some finite coupling between them, some finite tunneling, and this will hybridize two states. And I mean, this should somehow capture the problem. What we do not have here is what is a microscopic parameter, and we want to verify this now by making a microscopic theory based on simple classical analysis. Okay, so this is just a simple model, and we keep this result in mind to compare it then afterwards our findings to this. Okay, so having stated the problem and gained some intuition what we might expect, let's now use what we said last time. So let's consider the same classical limit. Yeah. So let's try to apply what we learned so far in the same classical limit. Path integral So if we want to apply this machinery, then the transition amplitude that we're interested in can be expressed as a sum over all classical paths connecting initial and final states with some fluctuation determinant, and then a phase vector which is just given by the classical action of the classical path. Okay? But if we now simply want to apply this method, we immediately arrive at the problem that I stated. Well, but then what are the classical paths? Are classical paths given that the kinetic energy is much too small to overcome the potential barrier. Okay, so if we want to apply this, we cannot simply follow our prescription because classically there are no paths connecting the two minima. And we could say here, okay, we are stuck, we don't know what to do, so we have to rely on other methods. But then the idea is, well, let's take really the series. Let's say we don't consider this as a real parameter, but let's consider some time of evolution and imaginary time. If we can calculate this in some special time direction, we just have to take the solution and see if this then makes sense to analytically continue to the value we are interested in. Okay? So this is the question then you want to ask. Well, is there, if we allow for a more flexible object, is there some then reference trajectories around which we can build up our semi-classical analysis? Okay? And actually, the hint, so I'll just put this generalizing time to be complex. Are there classical paths which are then paths in imaginary time, which can serve as a basis for the semi-classical analysis. So that's the question we asked, and actually the answer to this question was already given in the last lecture, because there we discussed the path integral representation for the density matrix. So where we have, instead of IT, we have here just the beta, or let's say some complex time. What we saw is that, well, you can still write it as a sum over, you can still express this as a path integral, which is given by the sum of all paths where you have the action, but this action now is not the action in real time, but it's the action in imaginary time. So what did change? We have here an I dt integral, this just becomes integral d tau. Then the action has a kinetic term, which is the velocity squared, q dot squared. Now, q dot is a derivative with respect to t, so if you generalize this to it, this changed the sign. So this is why we had an overall minus here. But then in the potential, you don't have this one sign change, because it's just then the potential d of q of tau. Okay? So you get a relative sign change in the kinetic and the potential energy parts. Now the relative sign change means what? Well, we just invert the potential. Okay? So that's the basic observation. If we look at the path integral in purely imaginary time, we kind of invert the potential. Now the inverted potential means we're trying to find classical solutions of the problem. A particle starting here, that's time 0, and ending here at some time t. So always in the path integral we fix the coordinates and the time, but we don't say anything about the initial momentum. So of course then there are plenty of solutions, or there are solutions we can look at. Okay? So that's the entire idea. If we allow this to be more flexible, we can do what is called like rotation imaginary time. It's called Wick rotation. which allows us, which is first of all a trick to invert the potential and to make this problem accessible to semi-classical methods. Okay, so that's all the idea, and this is often in the literature called the big rotation, which is here now considering specific imaginary, specific time, so not considering like general C, but just rotating it to the purely imaginary axis. Okay. So the basic idea is, okay, so this is just the general strategy: find solution by studying first of all a related problem, in imaginary time, and then to analytically continue solution to real times. So that's the idea of this replication. So to put it into formulas, that is, what we look at now is a transition amplitude or a transition probability in the end we're interested in, from minus A to A in some imaginary time tau, and let me just put here the index tau as we also put here to the action to denote this is now the probability in imaginary time, which we calculate as the matrix element squared of this object now, and then this is the object that we're interested in. And now, minus A. Yeah, thanks a lot. Minus A. So this we try to calculate, and then of course we have to make an analysis of this object. And the idea is, well, if this is an analytic function in the upper plane, we can just rotate it back to the solutions we are interested in. So if this, if P, here for example, analytic in upper half plane, the complex upper half plane, then we can just substitute into the result what we want, then we can get the probability for minus A to A in time t, just by taking the probability in imaginary time, minus A to A, and substitute t again by it. So if you want, what we calculate the amplitude and some purely, so I just invert, so this is now the purely imaginary axis, okay? So we calculate this. What we are interested in is in the real axis. So once we have found the solution here, and we see that there's no singularities, no problems arising here, we can just simply analytically continue this function here back to the real plane, to the real axis, and we have a result for this expression here. Okay? So that's the basic idea. Okay? Questions or? And again, so we just do this for an example, and this generalizes, and one thing one should always keep in mind is like the analytic structure of the objects that you're calculating.
Na exponencial vai ficar positivo ou negativo no formalismo de tempo imaginário?
O quê?
A probabilidade ali na exponencial de menos IH tal, aquele menos ali vai ser menos ou mais?
Esse é de menos A para A.
Na exponencial de menos H, Ele não mudou para positivo aí não? Por causa do tempo imaginário?
Não, na verdade...
Ou é porque a hamiltoniana já está escrita também?
Não, bom, primeiro o que você começa é com essa hamiltoniana, tá? Agora você faz analytic continuation, ou você estuda um problema que você pode solucionar. Agora, se aqui tinha um mais, você teria um problema porque não é estável, né? Aí você já teria um problema que isso vai te explodindo. Então, bom, é melhor começar desse problema com menos, que na verdade, se você pensa de tal sobre H como sobre temperatura, esse seria o problema que a gente falou na última aula, né? Que o beta, que seria identificando tal H com beta, isso seria a density matrix. Agora, se a gente, nesse objeto, depois bota I tal, em vez de tal, a gente chega de novo nessa expressão que a gente está interessado, tá? Mas sempre tem que pensar com isso, blá blá blá, se I tal menos I tal, sempre é um pouco confusão. Aqui não tem essa confusão porque se deveria começar com um objeto que é bem definido, né? Tá? Okay, so that's the idea. So the question is, well, what do we gain? And I already said it, but I still write it down. So what do we gain from studying this object? Well, this is just writing down what we had discussed last time. Always identifying tau over h bar with beta. Is that, well, we can express this as a path integral in imaginary time. So here we have the initial conditions, Q of 0 being at minus a and Q of tau being at a. And what we weight every path with is the imaginary time action divided by h bar. Okay, so this is the imaginary time action, and the imaginary time action, as said, has this important property here for us, that you have inverted the sign between the kinetic and the potential energy. So this is the form of the imaginary time action, which has here a plus and not a minus. Okay, and just so last lecture I always wrote Q dot over 2m. So that was like so there was m's all over the place roaming around in the thermal wavelength. So Guilherme afterwards came to me. So it was just stupid thing. Okay, so I hope. Okay, so but this is the idea. Okay, so we inverted the sign, and again we inverted the sign simply due to the fact that this contains a second derivative. Okay, so there's I squared appearing here, which doesn't appear here. Okay, so that is what we are considering now here. What we consider now is consider particle moving in the inverted potential. Okay, so instead of looking at this problem here that we started out from, we are now studying this problem here. Okay? So now what we should do, if we want to apply the semi-classical analysis, we have to look at all classical paths which are connecting minus a, and then after some time t, you arrive at a. Okay? We are looking at all the classical paths connecting these. And this obviously now is possible. So now we have classical path around which we can perform our analysis. So classical path from minus a to a in the imaginary time tau. Okay. So now we can just do our program and do the semi-classical analysis for this problem. And what we will see is that the object we then have to consider there is instantons. Any questions up to here? Okay, so now we just do our program, no? So this consists of 2 steps. Well, first we should do a classical analysis, which will identify the classical path and the classical action associated with the path, and see if there is more than one classical path. And then the second step is considering the quantum fluctuations, the Gaussian quantum fluctuations around classical solutions. So that's the usual procedure that we do. So let's start with the first part, and this will lead us to the notion of the instantons. So, let me see. Maybe it's good to first consider, I just briefly discuss here one example for potential, but all we are going to do is generic for all kind of double well potentials. It does not rely on the form, but to make it more illustrative. So to illustrate, let's consider one example, okay? First, so what we are considering is the potential here, double well potential. So this is at q plus and minus a has a minimum, and then it has quite a quantity term. So it gives rise to this. So if you just look at the classical solutions, so that's like still the general program. So what we want to look at is classical solutions. So this here denotes derivative with respect to space and this with respect to time. And you see that there is a sign different here. Okay, so that's all. I mean, that's the entire idea that here we have now inverted the sign, which allows us to find solutions. Okay, this is because we're considering imaginary time. So if you look at classical solutions, you will find for this kind of problem the following. So I should here I should always assume that the typical, so this is set around the maxima, which are now maxima, previously were minima, they have a typical like a harmonic oscillator. So there is some energy scale in the problem. So here would be lambdas times r squared, I guess, which then defines a time scale. And we will consider times, imaginary times, larger than this intrinsic time scale. Okay, so this is like given by the derivative at the minima. So this is, which is here symmetric, and then it would be the omega in the harmonic oscillator. Okay, this here, the omega. Okay, so here would be lambda times r squared. Okay, if you plug this potential in here, second derivative with this potential, you will find the following solution, provided that you're interested in this long time scale. So just write down the solution. So you can check this at home, but this is also just an illustration because we can make some observations here. So this, let's call now depends on tau prime. This is just a solution. So this depends on tau prime. Omega is fixed by the curvature of the potential close to the maxima. And we have some free parameter which I call tau 0. Okay? So this tau 0 is a free parameter here. And we have made the assumption that omega times tau, so tau prime is in between 0 and tau. Okay? So this omega times tau is much larger than 1, and also we assume that T0 in the same way times omega is much larger than 1. Okay, so this is assumptions here that from tau prime is from the interval 0 and tau, and we assume that tau 0 and tau are much larger than 1 over omega. Okay? Now, why did we use this? Well, you can see already if we set tau prime to 0, we have here minus omega tau 0. So this goes just to minus a. Okay? While if we take here tau and tau minus tau 0 much larger than omega, then this goes to a. Okay, so this is a solution which in this limit connects minus a and a in the time tau prime. Okay, so if we want to draw this, I might draw this here. This looks the following way. So here is the coordinate a and minus a, and we have a function here which changes in time tau prime from 0 to tau, from minus a to a. The transition between those two values is just given by this intrinsic time scale here. Okay, so this function is like constant for this being very large negative and positive, and once this becomes of the order of 1 over tau, this becomes of the order of 1 over omega, then this varies between the two values. Okay, so we have the width of this structure which is given by this intrinsic energy 1 over omega, and we have here chosen to be the parameter tau 0. It's not fixed, it can be anywhere respecting these conditions. Okay, so we have some free variable here in the problem, which is the time scale when you want to have the transition. Okay? So, if we are interested in this limit, like in the transition amplitude at large times, where large means corresponding to a transition in a time much larger than this intrinsic energy scale or time scale in the problem, then we find in this kind of in this specific example, this problem which has the following properties. Well, most of the time the particle stays at plus minus a, k q being plus or minus a, and only in a very short moment set by this energy scale 1 over omega, like on the time scale set by 1 over omega, it makes the transition, it changes position. Okay, so now I just say something that we are going to verify like in a minute for the generic case. So now what you want to do, once you have found the solution, you will, in the classical treatment, first calculate the action for this classical solution, because we have to insert the classical action. Now, if you insert the solution into the classical action, you will find that the classical action is just determined purely by the potential, by the functional form of the potential. So no dynamic information enters into the action. Okay? So just by the potential, we will shortly see this. Now this means that well, no dynamics is entering there. So this gives us some hope that this observation that, or this what we discussed here, the structure is more general. I come back in a minute. So just here in this specific case, and as I said, this will be generalized, what we observe then is kind of, we have some very well-defined structure in time. We have a transition at some specific moment which we can choose freely. And this happens in the limit we are interested in on a very short time scale. So we have a well-defined structure in time. So we can just say, well, this is in a way just like a particle, okay? This is a very well-defined structure in time. This is called the instanton, and we will consider it like this transition as some kind of particle. Okay, so we can position that anywhere, and we will consider this as a particle in a way that we come to. But let's just for the moment say that this changes position very quickly. So it is an instanton so it, in a way, happens instantaneously on the time scales that we're interested in. An instanton-like structure. No, an instant-like structure. Sorry, in time. And this is called the instanton. Now, just to take already ahead what we are coming to. So you see, if you allow kind of for then the tunneling going back again and forward again, you can see that you can have multiples of these transitions, which will always be separated by times where the particle sits at one of the tops. So in real time, this would correspond to the particle sitting in one of the minima, and then it suddenly makes a tunneling, stays again in the minimum, tunnels back. So the imaginary time, this would correspond to sitting on the tops and making instantaneous transitions, but can happen various times. So you can, in a way, say this is kind of a structure in time, which also has some kind of, let's call it charge, which is here going from minus A to A, because it could tunnel back again to the other one, to A again, so you would have another event here, you could, if you call this like an instanton, like a particle, you could call this the antiparticle, the anti-instanton, because if they collide, they will just annihilate each other. Okay, so this is like the idea why we might want to think of particles. Okay? But so far we have all discussed this here for one specific example, and I have given already one hint, which tells us that this might be more general, and this is, once we calculate the action for this object, this is independent of any dynamical information which tells us already that it's some kind of topological object. No? So what I now want to convince you is that this specific, like what we found for this specific example, is actually of more generic nature and holds in general and kind of physical arguments. Just say here, so this observation of having this well-defined structure in time is general, meaning independent of this specific example of considering this Q squared potential of this above example. So the general argument now comes. And it's again all of the observation. So we are interested in this transition amplitude, and we consider a specific limit where we're considering times much larger than the intrinsic time scale. So let's consider here this double ball potential, which is now worded, which might be any, specific. Doesn't have any specific form. We just want to have two maxima here. And what I said before, we have a microscopic timescale in the problem defined by the harmonic oscillator here. Okay. So here we have some microscopic energy scale defined in the problem, which gives us some time scale. And we are considering times larger than this. That's what we are looking at. Now, what we make is the following observation. So let's see, what we're interested in is, we're starting here with a particle at time 0, and we want to see like classical solutions where the particle makes a transition to here. Okay? So let me see. What we observed here is, well, in this limit, the particle sits nearly all the time at one of the minima and makes a transition at this time scale. So now we are considering a generic potential with this microscopic energy omega. And let's just ask, if this is generic, let's try to see, well, can we make an estimate of the typical time the particle needs to make this transition? And all we said here is, well, that this transition time is very short. Okay? So let's make an estimate of what is the typical time, let's call it, so what is the typical time for a transition? Or for passage, let's call it tau passage. Well, and now comes the main observation, which is actually not very deep, which is to say, well, if we look at the typical time the particle needs to go from here to here, well, obviously the highest velocity is down here. While here the velocity is the slowest, and here, the particle is the slowest. So the typical time scale the particle needs to propagate from here to here is actually the time it takes it to leave this maximum and then come back to this maximum again. Okay, so this should be the region which defines, in a way, the typical time scale. And this is now not considering factors of 2 or whatever. We just want to see what is, like, microscopically giving us the time scale for a passage. And this is just very simple. Well, the particle has to leave here, has to arrive here. Here it's going very quick, so it should be determined by this. Okay? And then we are actually there. If we accept this idea, then we just have to say, well, then what we need to do is to analyze the dynamics close to the maxima. So what we say here, well, it's actually all that determines how quickly the particle leaves and how quickly it arrives here again is only given by the curvature. Okay? So this is like considering an inverted harmonic oscillator and seeing how quickly it escapes from maximum. Okay? So we can entirely build an analysis on the inverted harmonic oscillator. Well, then, of course, the only energy scale that appears here is omega, and it's not such a surprise that this will determine then the time scale that is given there. But the observation is, well, most of the time the particle spends in the passage is here and here. So this curvature matters here. Well, it doesn't really matter because there it has the highest velocity. Okay? So this is now just formalizing what I said, but once we accept this idea, I mean, everything that comes now is not of a surprise, because at this point we throw everything out apart from the curvature. And then, of course, this is the only energy scale that can determine this passage time. So we say that this time is given by sum of these two times, the particle leaving and arriving, and again, we don't care about factors of 2 and whatever. So what we can do is we can look at the classical equations of motion for the inverted harmonic oscillator. No? So what we find then, I mean, just by simple algebraic manipulation, so we have q squared, m half, blah blah, we invert this, and this is now just given by plus minus omega times q minus a. And this then is, of course, no surprise, because what we expect, that the best solution then is just given, I mean, we should take the one which where we have exponential decay and not increase. So we find from this analysis that, well, the particle here exponentially quickly, or on an exponential scale set by the curvature, leaves here and similar here will then arrive there. Okay, so this is just a simple observation. So we say that the typical passage time is indeed given by 1 over omega, and this is general. This did not rely on the one specific form that we used here. So this means that this picture actually is generic for the problem we are interested here. Okay? So we verified this at one specific example, but this is generic. Everything is set by the curvature, and now we should still calculate then the classical action associated with a given path, which is then confirming what I said before, is that the action doesn't depend on the dynamical information. Maybe just make, yeah, it's not so much, but just make like 5 minutes break. Okay.